Section 19.5 derives the formula for delta G, which we will not do at this time. It's doable, but it's not really important that we derive it. It makes everything a little bit confusing. And I just want, all we really want from this equation is to know that this one formula combines the contribution of enthalpy and entropy, and how the entropy term is varied by the temperature. Okay. Also, we should know that if delta G is negative, it is spontaneous. If delta G is positive, it is non-spontaneous. That's all we have to know about that equation. Also, what does it mean when delta G is negative? In this reaction, N2 plus H2 makes the ammonia, just like we discussed before. If delta G is negative delta G, that means it's spontaneous. That means it wants to go to the right. Okay, so it wants to go to the forward. So the forward reaction is spontaneous. So in this case, you have the free energy here. It's going to go down. Spontaneous, meaning it's giving off that energy as it falls down in energy until it reaches a low. At this point, your system is at equilibrium. When delta G is 0, when the change in energy is 0, as given by the slope here, that means you're at equilibrium. Okay? If delta G is positive, as given by a positive slope going up, that means that the forward reaction is not going to happen. It's not spontaneous. Therefore, the reverse reaction is what's going to happen. It would rather go back. So if delta G is positive, the reaction is spontaneous in the reverse direction. Okay, so here is a very easy example of how to calculate delta G. So the formula is delta G is equal to delta H minus T delta S. Calculate the standard free energy, that's delta G, for the formation of NO using this equation. Given that delta H is 180.7, so you just plug it in there. Very easy. If they don't give you delta H, just do products minus reactants. Kilojoules, and it's going to be per mole reaction because they did products. Delta H, the formations of the products minus the reactants. Minus, don't forget the temperature here, 298 K. And also don't forget that they give you the delta S that we get from the chart is going to be in J, okay? So times 24.7 J over K. Okay, so, and again, you can, if they don't give it to you, you can do products over reactants using the thermodynamic chart here, using the S values here, okay? So then notice that the K's will cancel, but your unit's going to be J and this is KJ. So you have to have the same unit when you add things. So 1000 J is 1 KJ. And that will give you a number. Just calculate that. So I calculated 173.3 kilojoules, and then you can add per mole of the reaction. And the reaction is given up here. Once you get the answer, you really should understand what's happening here. First, you should know it's positive, meaning it is not spontaneous. Instead of getting energy out of it, you have to put energy into it. And the reason you have to put energy into it is predominantly due to the enthalpy term. Which term do you think is due to? Think. Which term do you think is due to that made this so not spontaneous? The enthalpy term or the entropy term? Okay, so if I look at the enthalpy here, I analyze it and it's positive. That means I have to put energy into the system. So the energy is on this side. I have to put energy in to make it go to the right. So automatically I can tell that's not really good, because if you have to put energy in, it's not too spontaneous. Okay, next, the delta S, even though I can't tell 1, that's 2 moles of gas, 2 moles of gas, they gave me delta S. Delta S is positive, which tells me that's good. That means it becomes more chaotic. If it becomes more chaotic, it'll drive the reaction to go forward. Okay, but how chaotic is it? It's not that much, because remember, this is 24.7 J. This is in kJ. So it's really 0.0247 kJ. Right? In the right direction. Now, if you get this hotter and hotter and hotter, the small positive value multiplied by a high temperature might be high, which would make this spontaneous with a negative delta G. But it's pretty cold. It's just room temperature, so it's still pretty bad. Okay, so what caused it to be non-spontaneous? I think it's because it's so endothermic. You can also get the standard free energy change by doing the same thing with delta G of products minus reactants. And when you look at the appendix C, the second column here, or the third column here, are the delta G of formation values. You can get it that way as well. Okay, and you do the same process, products minus reactants. So for this one, I am not going to do it. It's pretty simple. You just look up the chart. You do products minus reactants. Please use the textbook to go over that. Okay, let's see if I should do this one. Okay, this one's good. It says, we use test law to calculate delta H for the reaction. So they put delta H right there. And I'm going to think, oh, that's so exothermic. That means to me that the reactants had a lot of energy. They gave off that energy and became very stable. So this is good. It's good to be exothermic. So this will drive the reaction to go to the right. Okay. Let's look at delta S. They didn't give us delta S, so then I have to count for the moles. So I have 6 moles of gas becoming 3 moles of gas. And I have some liquid here, which means it was chaotic and became more ordered. So I think that it became more ordered. So what do you think is the sign for delta S? I think it's going to be negative. Okay, so if I were to predict, I'm going to look at the formula. Delta G is equal to delta H minus T delta S. Delta H is huge, negative 220,000 joules or kilojoules, minus, I'm going to put the temperature, depending on what the temperature is, delta S is, I don't know what it is, but it's probably going to be pretty small. It's in joules. Okay, so it's going to be negative, whatever it is. So what this tells me is this. As the temperature gets higher and higher and higher, this and this becomes positive. The entropy term is positive, which will make this not as exothermic. So I don't want high temperature. I probably want low temperature. If the temperature is low, this term, which is the entropy term, combined with that negative right there, becomes a small positive number. Small positive entropy term. So this huge exothermic product that you get, the energy that you get, is going to drive the reaction. Okay, now to predict that, it says predict whether delta G for the reaction is more negative or less negative than delta H. Predict whether delta G is more negative or less negative than delta. Oh, okay. So if this becomes positive, so it's not going to be as negative, so less negative. So let's say this whole thing is a -1 and a -10, so positive 10. So it'll be negative. If this were positive 10, so this would be a negative 210. So it's not as exothermic. So it would be less negative. That's what they mean. Okay, so now you're going to use the appendix C to calculate delta G. So delta G is equal to delta G products minus delta G reactants. I'm not going to show you the work there. Just check the book as well. But it's negative 210. Oh my gosh, look how close I got. 2108.25. So it's not as exothermic because you had to take away this part of it. And that unit is in kilojoules.